Good morning, everyone. Today, we're talking about the important topic of Thevenin and Norton equivalent networks or equivalent circuits. Okay. Um, Assuming or hoping that you have watched the lecture videos and at least had a initial crack at the homework. So let's start with the concept first. What questions do you have about the concept of Thevenin and Norton? Anyone? We have not looked at it yet. How many of you have attempted the homework 12? Have you already submitted it? Not yet. We haven't taken a look at it. How many of you have watched the lecture video and have questions? Okay, let me first start by saying that final exam, this will be one big problem of 32 points, about 30 points or so. All right, so I've been keep harping that this is a very important topic. Students need to pay attention to this. All right, it'll be like a 4-page question. 1, 2, 3, 4, 1, 2, 3. Yeah, about 4-page question that's going to test you everything from chapters 1 and 2. So it's going to ask you Thevenin and Norton equivalent circuits. That's the first thing you should know. Second thing about the learning is that this is not an analysis technique. Okay, this is something that I mentioned in the lecture video also. This is not a new analysis technique. This is a theorem. All we are doing is we're applying everything that we learned so far into developing this equivalent, so-called equivalent circuit. Okay, so this was a theorem. It's known as Thevenin's theorem. It was postulated by a French telegraph engineer in the late 1800s, I think around 1880 or 1890. His official title was commandant in the French army. His name was Leon Charles Thevenin. He postulated a theory about linear circuits, saying that if you had a large circuit comprised of hundreds of thousands of components, but only linear sources and linear elements like resistors, and if you took any two analysis terminals, you could represent that entire circuit as one single voltage source. So this would be hundreds or thousands. Or greater, or more. You could represent it as one single voltage source in series with a resistance. So let's say this is A, this is B, and between A and B, you could represent an entire circuit by one single voltage source. Essentially, if that circuit, which is a sealed box, has numerous voltage and current sources, okay, so inside this sealed box, we have several voltage and current sources. You could represent all of those sources as one single voltage source. The single voltage source is known as Thevenin voltage, and all the resistors in the circuit can be represented as one single resistance called Thevenin resistance RTH between the same terminals A and B. Hence, it is known as Thevenin's equivalent circuit. Again, it's an important concept in circuit analysis, but it's not an analysis technique. Okay, so you're not doing anything new here. What you're going to do is you're going to apply your techniques to determine the value of that Thevenin voltage. And you're going to apply your existing techniques to find the values for RTH, which is something you've already done. Any ideas or any guesses on how we can find RTH? Remember what I said. It's a representation, it's an equivalent circuit. It is a representation of a much larger circuit. We have one single resistance, and this circuit has hundreds of thousands of resistors. And we are finding one single resistance between two terminals. Where have you done that before? Beginning of chapter 2, to find REQ. You find REQ of a circuit, that is a Thevenin resistance. So again, it's not something new. It's something you've already done before. Thevenin voltage, again, this is something you have done before. Thevenin voltage is simply you're trying to find the voltage between 2 points in a circuit, and you can use any technique you want. You can use node voltage analysis, you can use mesh current analysis, you can use superposition, Ohm's law, KVL, KCL, any of the techniques that could apply for any circuit, and you're simply trying to find the voltage as measured between A and B. Okay, so again, repeating the same thing. Very important concept. However, it's not a new analysis technique. You're simply applying your existing techniques to determine the values of those two components on the right. Okay, and that is Thevenin equivalent circuit. So let's take a pause. Let me know if you have any questions. How many of you have already done the lab this week? Okay, already done. How easy was it to take the measurement? Or how long did it take for you to take those 3 measurements? Not that long, right? 3 measurements. But theoretical calculation takes a while. Does that make sense to everyone? Okay. And then we have Norton equivalent circuit. Norton equivalent circuit was based off of Thevenin circuit. Essentially, what Norton postulated was that you could take the exact same circuit with, again, several sources, including voltage as well as current sources. And you could represent it as a single current source. And this current came to be named after him, Norton current. This resistance sometimes is referred to as Rn, like Norton resistance, but most books you will see it's referred to as RTH. So the resistance is the same, RTH, Thevenin resistance. Again, it's an equivalent circuit, meaning you have a large circuit comprised of multiple voltage sources and multiple current sources, and you're representing all of it as one single current source. Okay, and that is Norton equivalent circuit. Again, Rn or RTH is the same thing. If we found Thevenin resistance earlier, that's the same thing as the Norton resistance in Norton current. The way to find Norton current is by taking your terminals of analysis, which in this case is A and B, and you place a short circuit wire between the two. And if your assumed polarity for A and B was plus at the top, then the Norton current direction must match. So if you find this short circuit current ISC, that is your Norton current IN. Okay. So again, the setup of the circuit is important. The analysis is something you've already done. Once you place a wire between the terminals, A and B, circuit changes, you analyze it using any method that you want, node voltage, mesh current, superposition, and the current that you find in that pathway between A and B is your Norton current. And the actual representation of the circuit, the final circuit, looks like that. And because these two are equivalents, the larger circuit, they are equal to each other. Okay. And the quantity that relates all three of them is Ohm's law. So VTH is equal to IN times RTH. In the final exam, I'm going to ask you to find all three quantities independently. Okay, no shortcuts. Meaning you find VTH independently, you find IN independently, you find RTH also independently. Okay. So that, in brief, is a explanation of what these two equivalent theorems are, Norton and Thevenin. Again, it's an important concept in circuit analysis, but it is not an analysis technique per se. After learning about these theorems, we can apply them to many different, many different circuits to analyze for other quantities. But in order to obtain these, we apply the techniques that we have already learned in the past. All right. Okay. So now let's go to the question that was asked earlier. 2.80. Okay. So you asked a question about this problem and you said, let's see. It asks us to find the Thevenin voltage, the Thevenin resistance, and Norton current for the circuit. Yes, all three quantities. Okay. So it is asking us to find VTH, Norton current, and RTH. So let's take our RTH first. Okay. So in Monday's quiz, what I'm going to ask you to do is to not analyze the circuit, but set up the circuit correctly in order to perform our analysis. Again, repeating the same thing that I've been harping on. This is not a new analysis technique. So the analysis is not something I'm going to assess you on. Okay. What is important is how you set up the circuit to determine these three quantities. So you need three different circuits to set up, or one for Thevenin voltage, one for Norton current, the other one for Thevenin resistance. So let's take Thevenin resistance first. How would we set up the circuit to determine Thevenin resistance? We have to modify the circuit. In the lab, what did you do? You took your meter and you connected at those output terminals and you measured Req. What did you do to the power supplies? We disconnected them and removed them from the circuit, right? So in this case, we see that there are two power supplies. One is a voltage source, the other one is a current source. In order to measure Req or calculate Req, there cannot be any sources left in the circuit. So we have to remove them. So to set up the circuit, if your setup is incorrect, nothing else matters after that, right? It needs to be set up correctly. So for RTH, I have a resistor here. And I have a resistor here. And I removed my sources from the circuit. Once I remove them, you have to replace them with something, okay? With voltage sources, if you remember superposition, what do we do with voltage sources? Does anybody remember? What do we do with voltage sources? Sure. Well, we don't short the voltage source, we replace the voltage source with a short. And so we place a short circuit wire right here. What do we do with current sources? The exact opposite. You open them or replace them with an open circuit, effectively resulting in just removal of the current source. That's it. So current source is no longer there. In the quiz or an exam, you don't have to draw those lines, but I'm drawing it out here for explanation purposes. We replace the voltage source with a short circuit, replace the current source with an open circuit. Now we take a few seconds, observe the circuit, and see how it has changed. We need to find Req at those terminals. So how has the circuit changed? What is the relationship between the 10 and 5 ohm resistors? They're in parallel because 10 and 5 are connected here, and they're also connected here at the bottom because of the short circuit. Again, this is a little tricky. Sometimes if you're looking at it from the perspective of the source, then the 10 and 5 are in series, especially if you're simply measuring the voltage across the 5 or 10 ohm resistor. But in this case, we are trying to find Req. Req is from the right. You're looking into the circuit. And so we have 2 points right there, and we are taking those measurements across those 2 points. Hence, 10 and 5 are in parallel. And so Req is 10 and 5 in parallel. Hence, our Thevenin resistance is 10 and 5 in parallel. In the quiz, I'm not asking you for the analysis. I'm not asking you to find Req. This is something we've already done. All I'm going to ask you in the quiz is for this. Set up the circuit. That's all I'm asking you. Okay. Thevenin voltage. What do we need to do for Thevenin voltage? Can we use the same circuit as we use for RTH? Okay. Can we use the same circuit? The answer is no. If you're trying to find voltage, just thinking logically, the circuit setup for RTH does not have any sources. It only has resistors. There is no energy source. If there is no energy source, there could not possibly be any voltage or current flowing in that circuit. Okay. So each circuit setup is independent of the other two. So with Thevenin voltage, we go back to our original circuit. We take our original circuit. And draw it out exactly as it is, along with all the sources and everything. So 1 amp, 5 ohms, 10 ohms, and 10 volts. And in this case, we are not looking at it from the perspective of any other component. Okay, this is an important point that I point out in the lecture video. Okay, so please again review those very carefully. All we need to do for Thevenin voltage is we need to identify our terminals of analysis. In this case, it's easy. Our terminals of analysis are right here. And so we need to find the voltage between these 2 points. And the open circuit voltage is our Thevenin voltage. Analyze using, again, let me point this out. In the quiz, this is what I'm asking you to do. Simply show me the setup of the circuit, no analysis required. Okay. For Thevenin voltage, there's nothing else to do except you take the original circuit as it is, assign a polarity for VOC. It does not matter what polarity you assign. Just follow logic. 10 volts has a positive at the top, and so logic dictates, or laws of physics dictate, current is flowing in the upwards direction, goes towards the right, and then hence then makes its way down in the circuit. So VOC will have a plus at the top, minus at the bottom. That's my assumption. But you can assume the other way around, doesn't really matter. Okay. In the end, your sign of the voltage must match the polarity that you've chosen at the top. So analyze this using any method of your choice, superposition, node voltage, mesh current, and determine that VOC. And that is your Thevenin voltage. Was your question about Thevenin voltage or Norton current? Norton current. Did you set up the circuit? All right, let's take a pause while this sinks in and let me know if you have any questions. So the question being asked is about clarification of the Thevenin voltage setup. And the answer was in the question, yes, everything is as it is. We do not change or modify anything. This is the same circuit. Yep, there's no need to redraw. The only case where we would redraw or make any changes is if there was a component between those terminals and the question asked, analyze and find the Thevenin or Norton circuit as seen from the perspective of that component. Then we would remove that component. So now we have open terminals, and then analyze the rest of the circuit. This is something I emphasize and I point out. Essentially, yes, because they're in parallel. So those terminals of analysis or terminals of interest are in parallel with 1 amp current source and the 5 ohm resistor. So you find the voltage across the 5 ohm resistor, and we'd have our Thevenin voltage. You had a question? Okay. All right, let's look at the setup for the Norton current. So same circuit. We go back to the original circuit. But now we need to find the Norton current. And the key word is current. Current needs a pathway to flow. So we place a short circuit wire between those two terminals. And this is the correct setup. Okay. Now, this is important. We have current, so we must assign a direction for that current. The direction of that current must follow the polarity of your chosen voltage. Oh, sorry, the chosen polarity of your voltage. So in Thevenin voltage, we chose plus at the top, minus at the bottom. So which direction is the current flowing? We have ISC we need to calculate, which is our Norton current. Which direction is ISC flowing, up or down? Anyone? Current always flows from high to low, always goes from plus to minus, except for a source. But this is not a source. So if you chose plus at the top and minus at the bottom, current must flow from plus to minus. So it's going down. So again, this is an assumption on our part, but the assumptions for both ISC and VOC must match. So this polarity right here and this current direction right here must match. And then this is the setup for the Norton current that I'm asking for. Okay, so these 3 circuit diagrams for that one single circuit is what I'm asking for in the quiz. That's all I'm asking. I'm not asking you to do any analysis. Okay, whatever circuit I give you, I'm going to ask you to find Thevenin voltage, Norton current, and Thevenin resistance. You just need to show me how you would modify the circuit in order to find those quantities. So these 3 circuit diagrams is all I'm asking. Does that make sense to everyone? No analysis required. Analysis is something you have done. I'm not assessing on those. If the setup is incorrect, the rest of your analysis does not matter. So setup is the most important thing for Thevenin Norton. No analysis. Okay. All right. So let's proceed. Question was asked about how to find Norton current for this problem. How do you think the circuit has changed? We can apply, first of all, we can apply any technique we want. We can apply node voltage. We can apply mesh current. We can apply superposition. We can apply any technique we want. How has the circuit changed? We have a short circuit wire that is in parallel with the current source. It is in parallel with the 5 ohm resistor. Effectively, if you have resistors in parallel with a short circuit wire, effectively that resistor is removed from the circuit. Because it's in parallel, any current that comes out from any of the sources has a path of least, has a pathway where R is equal to 0. If R is equal to 0, all of the current is going to go through that pathway. The easiest way to analyze this circuit is, well, I would say all three of methods will be easy. I could analyze this using NVA or MCA or superposition. Superposition will be quick. So if I analyze this using superposition, for the first one, I have my voltage source, I have a resistor, and then I have the short circuit current. Current sources are open, right? In superposition, only Vs is active. So the only thing left in here is the 10 ohm source. So this is ISC 1, which would be 10 over 10, using 1 amp. And if I analyze this using only the current source active, this is a short. This resistor is no longer part of the circuit. And I have a short this way. So current goes up, splits in two. This has a resistance of 10 ohms. This has a resistance of 0 ohms. So what do you think is the value for ISC2? 1. You can apply current division and prove it or calculate it. And the answer you would obtain is 1 amp because everything's going to go through there. So my total ISC is ISC1 plus ISC2 is 2 amps. You want to enter that into the system and see if it's correct or incorrect? You can, for practice, you solve this using node voltage, you solve this using mesh current, and you should be able to obtain the same answers. So again, use the same circuits and practice. Yes. Yes, at the top and at the bottom. Yeah. So if you said that as a reference, the answer would be 0. That is correct. So let's take a look at it. If I solve this using node voltage analysis, it's a very interesting. All right, we need to find this ISC. We're trying to solve it using node voltage analysis. Because of the short circuit wire, we only have 3 nodes in the circuit. Actually, all of that is one single node. So not even 3. There's only 2 nodes in the circuit. Let's take 5 seconds to look at the circuit. Because of the short circuit wire, there are only 2 nodes in the circuit. That's A and that's B. And we already have answers for everything. So if B is our reference, if B is the reference, VB is 0 volts and VA is 10 volts. So we already have the answer immediately. So now all we got to do is apply KCL. If you apply KCL, let's apply KCL at B. What do we have? We apply KCL at B. I have one current going this way, and I have ISC that's coming down, and so it's going this way, right? And then I have this 1 amp current that's also coming up into that node, right? So I have one current coming from the left, another current coming up from the current source, and then ISC is the total current. So if I apply KCL, let's call this IA. I have IA plus my current source of 1 amp is equal to ISC. IA can be expressed as VR1 divided by R1. VR1 can be expressed as VA minus VB divided by R1. VA minus VB is 10 minus 0 divided by R1 is what? 10 ohms plus 1. And so ISC is 1 plus 1, 2 amps. Same answer. All right, let's take a pause. Let me know if you have any questions. Let me know if there's something doesn't make sense, okay? The analysis portion is different for every circuit. Okay? There is no way to cover all everything. So every time we make a change in the circuit is going to change. The circuit changes, then analysis changes. Yes. Well, ISC, it's a good question. So question being asked is, if we use mesh current analysis, then wouldn't ISC simply be 1 amp current source? Not really, because that current source is in a shared branch. And because it's in a shared branch, if I solve this using MCA, ISC. So now I'm keeping that resistor in there, but again, we may as well not have it. So we have IA, IB, and IC. So IC would be ISC, that is correct, right? ISC would be my mesh current IC. However, IC is not the 1 amp current source. Okay. IC minus IB is equal to my current source of 1 amp because it's in a shared branch. As long as the current is in a shared branch, cannot have the same value as one mesh current. Okay. Because I chose my direction IC as going up and IB is going down. Question being asked is, why is it IC minus IB? Is because IC is going in the same direction as the current source, 1 amp, and IB is going in the opposite direction. If both were going in the same direction, it would be IB plus IC. If both were going in the opposite direction, I would say minus IB minus IC is equal to 1. And in this case, IB is not even necessary. Because of the short circuit, that middle resistor is no longer there, or effectively redundant. And so you can just say one mesh. So we can just say IA. 2 mesh currents, that's it. We don't need to have 3. Okay. And again, it'd be like one standard equation. Okay, so we were able to do one problem today, but I'm going to ask you, if you're going to come to class on Friday, please look at the lecture videos, attempt the homework, and then bring your questions to class. Okay. So we'll end class here today, and I will see you all on Friday. I will most likely extend the deadline for the homework till Friday. Okay. So I'll extend it till Friday. It's 22nd, so 23rd, 24th. I'll make it due on the 24th. Make sure you at least attempt the homework before Friday. All right. And then quiz on Monday.